Hi guys, Daniel here. Hope you're doing well. Hope you guys are studying hard. So today we've got paper 3 of the June 2023 series for A-level Maths Edexcel statistics. And yeah, having done this paper, definitely feel it was pretty much okay. There was a few tricky parts. You guys will have the timestamps in the description, so you can just quickly easily navigate to whatever question you'd like. I'm sure a lot of you go to question 6 with the integration. And yeah, that's pretty much it. And I've also got the past papers for paper 1 and paper 2 out on my YouTube channel as well. So I'll put a link in the description for that as well. But yeah, that's pretty much it. Let's get into it. Okay, so question 1 says the Venn diagram where P and Q are probabilities shows the three events A, B, and C and their associated probabilities. So we've got the diagram here. And then for part A, it just says to find the probability of A for 1 mark, which is not too bad, very straightforward. So the probability of A is just going to be the sum of all of the probabilities in this circle here, right, for the region of A. So therefore, the probability of A would just be probability of A, right, part A here. Probability of A would just equal to 0.13 plus the 0.25, which is just equal to 0.38. Perfect. So that's part A. And then part B says find, or not that, it says the events B and C are independent. Find the value of P and the value of Q. Okay, so remember independence, right? If two events are independent, it just means that the intersection is equal to the product of the two probabilities individually. So in other words, we could say that the intersection of B and C, like this must be equal to the probability of B times the probability of C if they're independent, which they are. So all we're going to do is just find out what these probabilities are and then plug these into the formula and then hopefully be able to find an equation in terms of P or Q and so on and so forth. So let's go ahead and do that. So the intersection of B and C would be right here, this 0.3. So I'm going to put this on the left-hand side. And then this will equal the probability of B, which is all of these probabilities added together. So 0.3 plus 0.5, which is 0.35, plus the 0.25 will be 0.6, isn't it? So this will be 0.6 here. And we're going to multiply this by the probability of C, which is the 0.3 plus that P, isn't it? This is the entire circle of C. So it'll be 0.3 plus P. And this gives us an equation in terms of P, which we can solve quite easily. So I'm going to divide both sides by 0.6. So we have 0.3 over 0.6, and this will equal 0.3 plus P. And then 0.3 over 0.6 is just a half, isn't it? 0.3 is half of 0.6, so this is a half. And then this will equal 0.3 plus P. And then taking away 0.3, a half is the same as 0.5. So I have 0.5 take away 0.3, which is equal to P. So that just tells us that P is just equal to 0.2. And now if P is 0.2 and we need to find Q, well, Q is the remaining probability. We know all probabilities sum to 1. So we're just going to add all of these probabilities together, take it away from 1, and that will give us Q. So let me go ahead and do that. So I'm going to say for part, no, not for part B because it's still on B. So for Q, we're going to add all of the other probabilities together. So I write sum of all other probabilities. I'll do this here. This will give us the 0.13 plus the 0.25 plus the all of these here, which is 0.05 and 0.3, 0.05 and 0.3, and then plus P, isn't it, which is 0.2. And then we're going to add these up and take it from 1. So I'll go ahead and do that. This will give us 0.13 plus 0.25 plus 0.05 plus 0.3 plus 0.2. This will give us 0.93. So this is equal to 0.93. And that tells us that Q is just equal to 1 minus 0.93, which is just 0.07, isn't it? So we now have P and Q, so that's fine. So that's part B done. Now part C says we need to find the probability of A given that B doesn't happen. So remember, this is just conditional probability and there's a formula for it. So the probability of A given that B happens, right? It's just a normal formula. This is equal to the intersection of A and B out of, right, the probability of B, isn't it? Because you need the probability of A if B happens. So it would have to be out of the probability of B. So this is the formula here that you should know. And then obviously they've asked us for the complement of B. So we're just going to put a dash in the formula, meaning that we're going to put a dash everywhere we see a B. So put this here, put one here, and put one here. So what we need to work out is where is the area for the probability of not B, right? Which is just going to be everything on the outside of B, which is just going to be, if I look at the diagram, it's just going to be these here, isn't it? This is the region where B doesn't happen. So that would be on our denominator. So it definitely would be 0.13 plus Q and P. So I'll do this here. So on the denominator, it's going to be 0.13 plus Q, which was 0.07, plus P, which was 0.2, right? And then on the numerator, I need the intersection of A happening and B not happening. If I look at the diagram, the only place where A happens and B doesn't happen at the same time is just at 0.13 here. So therefore, I'd have 0.13 here. So this will give us our answer, and then we're just going to plug this into the calculator and see what it will give us. So I'll go ahead and do that. So it'll give us 0.13 over 0.13 plus 0.07 plus 0.2. Just double check 0.13, yeah, that's fine. And this gives us 13 over 40, or press SD, 0.325. And that will be our answer for part C, and that is question 1 finished. Okay, so question 2 says a machine fills packets with sweets and 1/7 of the packets also contain a prize. The packets of sweets are placed in boxes before being delivered to shops. There are 40 packets of sweets in each box. The random variable t represents the number of packets of sweets that contain a prize in each box. Part A says we need to state a condition needed for t to be modeled by the binomial distribution where n is 40 and p is 1/7 for 1 mark. Okay, so this isn't too bad. So this question here is just asking you to remind yourself of the conditions needed for a binomial distribution. There are 4. First one is that there is a fixed number of trials n. Second one is that there are 2 possible outcomes, success and failure. The third one is that there is a fixed probability of success p. And the fourth one is that the trials are independent of one another. So what you need to do pretty much is just use one of those bullet points to just pretty much comment in context of this scenario here. So what I could talk about is the probability of a packet containing a prize that has to be fixed. Or you could just say, due to the fact that the packets of sweets are placed in boxes, they need to be placed independent of one another and need to be placed at random. So something like that. So I'll just say for the first one, I'll just say for part A, a condition would be that the probability of a packet containing a prize must be fixed / constant, whatever word you want to use. And that will give you the 1 mark. So that's done. So part B, let's go to it. It says a box is selected at random. Using this binomial distribution here, where n is 40 and p is 1/7, find the probability that the box has exactly 6 packets containing a prize. Okay, so this isn't too bad, so I'll just do this here. So we've got t is binomially distributed with n is 40 and p is 1/7. And we need for the first one, we need the probability that the box has exactly 6 packets containing a prize. So exactly 6 packets, right? Well, that just means that we're dealing with a point distribution, right? So they're asking us for p, the probability of t equaling 6. That's what we're looking for here. So you're just going to put this into your calculator. So this is just pretty standard stuff. So I'm going to go to menu. I'm going to go to number 7 distribution. And I'm going to go to binomial PD, aren't I? Point distribution, because it's t is equal to 6. And then you're going to plug everything here. So we've got x is equal to, we've got n is equal to 40. We've got p is equal to 1/7. So we're 1 divided by 7 here. And this gives us 0.173 to 3 significant figures. 0.173 to 3 significant figures. And then double I, what does that say? It says we need to find the probability that the box has fewer than 3 packets containing the prize. So fewer than 3 is just the probability of t being less than 3. Now remember, because we're dealing with a binomial distribution where we know we're dealing with discrete data, right? We need to say that this is just the same as probability of t being less than or equal to 2, right? So this is what we need to work out in our calculator. So I'll go ahead and go back to the distribution here. And then binomial CD, I'm going to use commutative distribution because I'm dealing with an inequality. And now I'll go for 1 and then 2 variable. And then I'm going to plug in 2 here instead. And then put this in. And then this will give us 0.0616 to 3 significant figures. 0.0616. And that will be our answers for that one. And let's look at part C. It says Camille's sweet shop buys 5 boxes of these sweets. Find the probability that exactly 2 of these 5 boxes have fewer than 3 packets containing a prize. Okay, so this one here is a typical question that comes up. So they start you off with a normal binomial distribution question. They ask you to calculate some probabilities, and then they give you another scenario. And in that scenario, they're asking you for another probability. But if you look at it very closely, it's something that you've actually seen before. So we can see that we've got the probability of having fewer than 3 packets containing the prize, right? Where have we seen this before? We've seen this right here, the top here. Fewer than 3 packets containing the prize. These are the same thing. So what's happening here is essentially is that they're just giving you another binomial distribution question, where in this case your n is going to be the 5 boxes of sweets, and your probability is just going to be the probability of you getting fewer than 3 packets containing the prize. So that's what you're going to do here. So what I'll do for part C is I'll just do it on the next page just so there's room. So for part C, we're going to say we're going to have a new random variable k, right? And this is going to be the number of boxes containing, let's just double check, number of boxes containing fewer than 3 packets. Yeah, fewer than 3 packets. Right, that has a prize, containing a prize. All right, so I'll just write this here. So we're just going to say then that we've got a k is binomially distributed, right? In this case, remember, there were 5 boxes that Camille bought, right? So 5, and it's going to be 5. Your probability P is going to be the probability of you of a box containing fewer than 3 packets, right? And that was equal to 0.0616. So that's going to be our P here, 0.0616. And then now the question asks us to work out the probability that exactly two, again, we know what that means. That is just equaling 2. So we're just going to work out the probability of k equaling 2. So I'm going to put this all into the calculator, see what it gives us. So now I've got 0.0616 here. Now I'm very pedantic when it comes to just very extra when it comes to dealing with approximations, right? So I'm not going to put in 0.0616. I'm going to put this whole value in here into my P for the binomial distribution. So I'm going to go back to normal distribution, and I'm going to go to binomial PD4. I'm going to go to variable, and then I'm going to put 2 in, which is already done. And then I'm going to put in 5 for n this time. And then for this, I'm going to put in answer. And that will give us that 0.06 number, right? And then plugging this in, this gives me this here. And to 3 significant figures, that would be 0.0313, isn't it? So the answer will be 0.0313. And that will be our answer for part C. So that's done. And then part D says Camille claims that the proportion of packets containing the prize is less than 1/7. A random sample of 110 packets is taken, and 9 packets contain a prize. Part D says we need to use a suitable test to assess Camille's claim. You should state your hypotheses clearly, and you should use a 5% level of significance. Okay, so this is just a typical hypothesis test question whereby, remember what you're doing here. They give you some sort of scenario, and you have a sample, and then you've got some observed value. You're going to find the probability of observing that value, assuming the null hypothesis to be true. Now, once you figure out what that probability is, your test statistic, you compare it to your significance level. If it's less than the significance level, you reject the null hypothesis. You say that that's statistically significant, and you accept H1. Or if that test statistic, the probability of that observed value is greater than your significance level, you accept H0 and reject H1. So just remember that. But yeah, let's go ahead and do this. Let me just screenshot this here. So we have it. We don't need to keep going up and down. So in our case, we're going to start off here. Let me just put this here. Okay, so we've got this here. We're going to start off by saying that H0, right? H0 is going to be the probability of the packet containing the prize, which we assume was 1/7. That's what we knew originally. And the alternative is Camille's claim, and it's less than 7. He's saying the proportion is less than, so it's going to be P is less than 1/7. And this is a one-tailed test, isn't it? And yeah, what do we do now? We're going to assume the null hypothesis to be true, meaning that we're going to have a binomial distribution here, where your sample size, in this case, was 110. So I'm going to put 110 here, and then the probability is 1/7. And then what you always should look out for is that observed value. It says a random sample of 110 packets is taken, and 9 packets contain a prize. So I always write out what the observed value is. So the observed value in this case, is just equal to 9. So what you need to work out is the probability of x being less than or equal to 9, right? I always do it as this. Well, it's one tail, then it's less than, so the probability of those is always going to be less than. These two inequalities are always going to be in the same direction. And yeah, so we've got this here, and then you need to work this out. And then once you work this out, you're going to just compare this to your significance level. So I'll just write, all right, significance level, we know is equal to 5%, which is 0.05. So yeah, let's go ahead and work out what this is and see what we get for it. So I'm going to put this here. I'm going to go back to menu, distribution, and then binomial CD, cumulative, and then variable, and then our x is 9. Our sample size was 110, and our probability was 1 divided by 7. So plugging this in, this gives us this number here. This is 0.0, and then let me just get it again. 383, isn't it? 383. Yeah, that's fine. And then you compare this with your significance level, which is 0.5. And as you can see, this is clearly less than 0.05. So what you would do here, now that you've compared them, we've got it less than 0.05, our significance level, you're going to say this is statistically significant. So, all right, statistically significant. I'll just write significant here, and that means that we're going to reject H0, and we're going to accept H1, the alternative hypothesis. Now, to get the final mark, you just need to comment in context with your findings, right? About your findings. So what we're going to say here is that based on the evidence we can see, there is evidence to support Camille's claim, right? Camille's claim. And what was Camille's claim? Camille's claim was that the proportion of packets containing a prize is less than 1/7. So you could just say there's evidence to support Camille's claim that the proportion, all right, prop for short, of packets containing a prize is less than 1/7. And that would be it. That would give you the 4 marks for this. And yeah, that's pretty much it for question 2. Okay, so question 3 says Ben is studying the daily total rainfall X millimeters in Leeming for 1987. He used all the data from the large data set and summarized information in the following table. So we've got our table here. We've got the recorded rainfall at the top, and in X, and then we've got our frequencies on the bottom. Part A says we need to explain how the data will need to be cleaned before Ben can start to calculate statistics such as the mean and standard deviation. Okay, so this is a large data set question, right? And what you want to do with these types of questions is make sure you just read up on the large data set, just get some general facts and figures for this large data set, right? Now, if I look at the question, it's asking us about how it needs to be cleaned. If you look at the table, we can see that I've got this TR at the end here, and this TR stands for trace. And what this means is that any data for the rainfall that was recorded to be less than 0.05 millimeters was recorded as a trace. So the data is not actually there. So to answer the question for how it will need to be cleaned, you just have to say that the values of the trace will need to be replaced with a numerical value. That will give you your first mark. The second mark will be to then suggest a suitable value for it to be replaced with. So let's just go ahead and do that here. So we got part A. Move this here. We could say that we need to replace the trace with a numerical value, right? That will give you 1 mark. The second mark would be suggest a suitable value for it to be replaced with. So you could just say, as the trace, right, is in between 0 and 0.05, because remember, anything less than that, right, we could replace the trace with, you could just do the average between the two because you don't know what value it is. It's safe to do the average. Or to be fair, in the mark scheme, it says that you can just choose any value between 0 and 0.05. So anything here would be fine. You could use 0.025 or any value. You could use 0 or 0.05 and so on and so forth. So yeah, that will give you the mark. That will give you the 2 marks for part A. Now part B says that using all of the 184, using all 184 of these values, Ben estimates the sum of x to be 390 and the sum of x squared to be 4,336. Part B says we need to calculate estimates for the mean daily total rainfall and the standard deviation of the daily total rainfall. Okay, so this isn't too bad, right? So this is just dealing with simple calculations, right? So B part I says we need to work out what the mean is. Now the mean, remember, it's just going to be equal to the sum of all of the x values divided by n. Now, in our case, they've told us that there are 184, but even if they didn't, you could just add up all of these frequencies and you would get 184 too. You can check that if you want. But yeah, so let's go ahead and do that. The sum of x was equal to, I think it was 390. Yeah, it was 390. And n is 184. So therefore, we're just going to plug this into the calculator. So I'm going to do 390 over 184. And this gives us 195 over 92. Or to three significant figures, this is equal to 2.12, isn't it? 2.12. So this would give you your answer for the mean. And then we need the standard deviation now for part B, double I. So just right here, double I here. And this is going to be equal to the square root of, I always remember it as the mean of the squares. So sum of x squared over n minus the square of the mean. So like this here. And yeah, so we're just going to plug this in now, plug in our values and see what we get. So the sum of x squared, I remember, was 4,336. N is 184. And then the mean, right, is this value here. But I'm going to just choose this fraction here, aren't I? So 390 over 184. And I'm going to square this. So we plug this into a calculator and just give the answer. So let's go ahead and do that. This is going to be 4,336 over 184 minus 390 over 184 all squared, and this is equal to 4.367 blah 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 to three significant figures. That would just be 4.37, isn't it? So I'm just going to put 4.37 here, and that'll give us the answer for the standard deviation. Okay, so that's done. Now part C says Ben suggests using the statistic calculated in part BI to estimate the annual mean daily total rainfall in Leeming for 1987. Using your knowledge of the large data set, give a reason why these data will not be suitable. Again, so it's very, very important that once you get to your exam just a couple of weeks before, just read up on the large data set, right? What you will know is if you read up on it is that the daily total rainfall, or all of the data, is just recorded between May and October, right? So since it's recorded between May and October, what you would need to say is, well, if you want to estimate the annual mean, that's definitely not going to be suitable because we're missing a couple of months. We're missing the months from November to April, isn't it? So you could just say here for C part I, you could say for C part I, C part I, that the data is recorded for, let me just make sure my handwriting is really, really neat, months from May to October. So an annual, underline this, an annual estimate would not be suitable. And that will give you the 1 mark. And then double I, what does that ask for? It says, state given a reason how you would expect the estimate in part B I to differ from the actual mean daily total rainfall in Leeming for 1987. So again, we need to acknowledge the fact that that it's only for months May to October, right? Now, if we want an estimate for the annual mean, right, how would that differ? Well, another thing that you should know, just general knowledge, right? And I'm sure some of you do geography, is that on average, the rainfall is highest in the winter months in the UK. So due to the fact that we don't have, for example, November and December, that would obviously skew the data, isn't it? It will skew our estimate, right? So we would expect the actual estimate for the annual rainfall would be larger than what we figured out in part BI because we only had months May to October. And obviously because of the fact that on average the rainfall is highest between November and December, you'd expect our calculation to be an underestimate. So you just say, just to finish, you can say on average, highest months for rainfall in the UK is winter. You could just write November and December. Since we are missing these months, our answer to BI would be an underestimate. So let me just underestimate. Okay. And that will give you the second mark in part C. Hopefully my handwriting is legible. Apologies, it's very hard to write on a graphics tablet. But yeah, that is our question 3 done, and that will give you the full marks. Okay, so question 4 says a study was made of adult men from region A of a country. It was found that their heights were normally distributed with a mean of 175.4 centimeters and a standard deviation of 6.8 centimeters. Part A says we need to find the proportion of these men that are taller than 180 centimeters for 1 mark. Okay, so this isn't too bad. So we've got a normal distribution here. So I'm just going to say for part A, I'm going to say X is normally distributed with the mean to be 175.4. And the standard deviation is 6.8. So I'm going to put 6.8 squared here. And then we just need to work out the portion of the men that's taller than 180. So greater than 180, in other words. So we're just looking for the probability of X being greater than 180, aren't we? So putting this into the calculator, you're just going to go to menu, you're going to go to distribution, you're going to go to normal CD. And our lower bound is going to be 180. And the upper bound, I always just choose a really big number, so 10 to the power of 10, right? And then the standard deviation is 6.8, and the mean is 175.4. So putting this in, this gives us this number here, which is 0.249 to 3 significant figures. So 0.249 to 3 significant figures. That's done. Now part B says a student claimed that the mean height of adult men from region B of this country was different from the mean height of adult men from region A. A random sample of 52 adult men from region B had a mean height of 177.2 centimeters. The student assumed that the standard deviation of heights of adult men was 6.8 centimeters, both for region A and region B. Use a suitable test to assess the student's claim. You should state your hypotheses clearly. Use a 5% level of significance. Okay, so again, this is a hypothesis test question, and we know how they work. You have some sort of scenario here, and they give you some observed value. You find the probability of observing that value given the null hypothesis to be true, and you just compare that to your significance level, right? So we're dealing with a hypothesis test for the mean of a sample, right? So what you'd want to do is say, okay, well, remember, if I have a normal distribution and we've got the mean mu and we've got the standard deviation to be sigma, so it's sigma squared here, then if I'm dealing for a sample size, it's just going to be n, it's going to be mu here, and then it's going to be sigma squared over the sample size, right? So it's what you're going to be, this is what you're going to be dealing with here. And we're dealing with region B, aren't we? Right? So if I was to do this here, then we're going to say we've got B, and it's normally distributed with the mean. We always assume the null hypothesis to be true, and it was 175.4, isn't it? So 175.4, and then it's going to be sigma squared, so 6.8 all squared over n, and in our case, n was 52, and they told us that the standard deviation was the same anyway. Yes, that's fine. So, whoops, sorry, that is for the original, right? And then for the sample size, it's going to be B hat, and it's going to be the exact same thing, 175.4, and then 6.8 all squared over 52. That is what we're going to be dealing with. This is just your original, and then this is your sample, right? So again, let's look at the question. It says that a student claimed that the mean height of region was different from the mean height of a region in A, right? So this is a two-tail test, isn't it? Because it doesn't say it's less than or greater than, it's a two-tail test. So in that case, we're going to say that our null hypothesis H0 is going to be mu is equal to 175.4. And because they've said it's different, it's going to be mu is not equal to 175.4. So this is a two-tailed test. And remember, when we have a two-tailed test, we half our significance level. So the significance level was 5%, which is equal to 0.05. So we have to divide this by 2 to give us 0.025, isn't it? So what we need to do now is calculate this probability here. Now, what did they say? They said that the observed value was 177.2. So let's just get a normal distribution curve going. We know that we assumed the null hypothesis to be true. So the mean was 175.4. And the observed value here was 177.2, isn't it? Which is somewhere here, right? Say this is 177.2. What we need to do is work out the area here, which would be the probability, and then we compare this with our significance level, right? If this is less than the significance level, then we reject H naught and accept the alternative. If it's greater than, then we accept H naught and reject the alternative. So we just need to work out what this area is here. This isn't too bad. So we're just going to be working out the probability of B being greater than 177.2 with this distribution here. So I'm just going to put this into the calculator and see what I get. So going back to menu and then distribution and then normal CD. And then the lower this time is going to be 177.2 and the upper is going to stay the same. And whoops, need to go back. That's not what I want. Go back here. And then the standard deviation, remember, is going to be the square root of this here, isn't it? Which is going to be 6.8 divided by the square root of 52, isn't it? So it's just going to be 6.8 over the square root of 52. That would give us our sigma here. So putting this here, it's going to be 6.8, right? Whoops, 6.8, and then divided by the square root of 52. And this gives us this here, and then the mean is, 175.4, so that's fine. So then I get this number here, right? And this is the value that we compare. So 0.0, and then what it was 28142, blah, blah, blah. 28142, blah, 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 right? And what we need to do is we need to compare this with our significance level, which is 0.025, right? So what we could say here is from here, we could say that 0.028142, blah, 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 is greater than 0.025. And remember, if it's greater than, then this is an insignificant, this is statistically insignificant. So we accept H naught and reject H1. So you're just going to say, you're going to accept H naught, and you're going to reject H1. And then remember, to get the final mark, you just need to contextualize it. So what was the claim? So a student claimed that the mean height was different, right? So you could just say that there is no evidence to support the student's claim. Yeah. So all you could just do here is just say that there is no evidence to support the student's claim. And that will give you the marks. So that's pretty much it. You just get your significance level, compare it to your value that you get when you do the probability, and then depending on whether it's less than or greater than, determines whether you accept or reject the null hypothesis. In this case, we had to accept it because it was greater than 0.025. And that's pretty much it for part B. And then part C says we need to find the p-value for the test in part B. So the p-value is just the same as the actual significance level. And that's just always equal to the value that you calculate here, right? Now, remember, this was a two-tailed test though. So you've got to be very careful. So this is not going to be an answer because on the other side, you're going to have that exact same one over here, that exact same area. So you're going to have to multiply it by 2. So these here are both 0.028142, blah, blah, blah. So I'll just do it. How much room do I have? I'll just do it here. So for part C, I'll just say p-value would equal 2 times that number there, 0.028142, blah, blah, blah. And I'll just put this in my calculator and see what it gives us. So what I'll do is I'm just going to go back to this here. If I click answer, I've got that value there. So I'm just going to do 2 times answer. This gives us 0.0563 to 3 significant figures. So it's just going to be 0.0563 to 3 significant figures. Let me just double check that again. That's fine. and that will give you your answer for part C. And yeah, that is question 4 finished. Okay, so question 5 says Tissam is playing a game. She uses a ball, a cup, and a spinner. The random variable x represents the number the spinner lands on when it is spun. The probability distribution of x is given in the following table, where A, B, C, and D are probabilities. To play the game, the spin is spun to obtain a value of x. Tissam then stands x centimeters from the cup and tries to throw the ball into the cup. The event S represents the event that Tissam successfully throws the ball into the cup. To model this game, Tissam assumes that the probability of S given that x equals x happens is k over x, where k is a constant, and the probability of the intersection of S and x equals x should be the same whatever value of x is obtained from the spinner. Using Tissam's model, show that C is equal to 8/5 B. Okay, so what I've done is I've just summarized everything here, just screenshot the main parts that we need for part A, right? So we need to show that C is equal to 8/5 B, and they've given us this information here, right? We've got the table, we've got the assumptions here. Now, when I look at these assumptions here, the thing that that's glaring to me, is the fact that they've told us that the intersection is the same, whatever value of x is obtained from the spinner. So I think that's probably what we're going to need to use to show that C is equal to 8/5 B, because what that means essentially is that, for example, if I have the probability of a S, and then let's say, for example, x is equal to 20 here, right? This must mean that this is also the same as the probability of S and the intersection of x is equal to 50, for example. These must be the same based on the second bullet point. Now, because we need to show that C is equal to 8/5 B, for me, it makes sense to use C and B instead of any just two random examples. So I'm going to rub these out. I'm going to rub this out here. And then I'm going to put C on the top here. And I'm going to put B here. B here. And then, well, C is when x is equal to 80. So I'm going to put 80 here. And then B is when x is equal to 50. So we've got this equation here. So pretty much what we need to do is work out what these are, and then hopefully that will give us C is equal to 8/5 with a little bit of algebra. So the question is, how do we actually get these expressions here? Now, when I look at these two bullet points, right, I've got a conditional probability of two events, and then I've got the intersection of those same two events, don't I? Now, for me, when I look at this probability, I ask myself, well, do I know any formulas that connect those two? A conditional probability of two events in the intersection. And that's just a probability for conditional, that's just a formula for conditional probability, isn't it? Which we know is that the probability of A given that B happens is equal to the intersection of A and B divided by the probability of B. And then if I rearrange this to get the intersection, this just means that the probability of A given that B happens, so given that B happens, multiplied by the probability of B, so just times them by the denominator, right? This is just equal to the intersection. So if I apply this with the events that we have, S and X is equal to X, right? This just means that the probability of S given that X equals X happens, right? Multiplied by the probability of X equals X, this has to be equal to the intersection, right? So we can use this to work out these expressions here, can't we? So let's have a go at doing this then. So let me just zoom out a bit so we can see all of the work in here. So for example, let's say I wanted to do C, right? We know that for C, we know that X is equal to 80. So what that means then is that using this formula on the right here, that means we're going to have probability of S and then X is equal to 80 multiplied by the probability of X equaling 80, right? This will give us the probability of the intersection like this. And this is for C, isn't it? So plugging everything in now, well, if I look at the first bullet point, we know that the conditional probability is always equal to K over X, right? So in this case, this one here is just going to be K over 80, isn't it, right? If I just use this formula right here. And then I'm going to times this by whatever the probability is for X equals 80, and that is C. So I get K over 80 times C is equal to the intersection, like this here. And this is for C, right? Now for B, I'm going to say X is equal to 50, right, from the table. So we get this here. And this will give us the probability of S given that X is equal to 50 times by the probability of X is equal to 50 is going to be equal to the intersection of S and X is equal to 50. And this is for B, isn't it? Now, if I plug in everything that I know, if it was K over 80 for when X was equal to 80, this is just going to be K over 50. right? Times by x is equal to 50. Let's go back to our table. This is b, isn't it? Yeah, so we're going to say we've got this here. And this is equal to the probability of s, and then x is equal to 50, right? Now remember what we know. We know that these two are the same because of this assumption here, this second bullet point. This is the same throughout. So that means that we can just equate these two, can't we? So if I equate these two, then we're going to have we're going to say we've got k over 80 times by c. This is going to equal k over 50 times by b. Now, I've got two k's either side. They can cancel, so I get 1 over 80c is equal to 1 over 50b. And then if I times both sides by 80, I'm going to get c is equal to 80 over 50b. And then the 10s will cancel, zeros will cancel. I'll be left with c is equal to 8 fifths b. And that is part A. And that was 2 marks. So yeah, we've done that. That's pretty much how we do that. Now, we've done part A. Part B says for 5 marks, find the probability distribution of x. Now, to find the probability distribution of x, that just means we need to figure out the probabilities here. And that's just, we need to figure out what A, B, C, and D are, right? Now, the first thing that you should always do is remember you're dealing with a probability distribution. So I'm going to say part B, we know that the probabilities must sum to 1. So I'm going to write A plus B plus C plus D is equal to 1, right? Now, what do we know so far? We know that C is 8 fifths B. So I'm going to just replace that there. So I've got A plus B plus 8 fifths B plus D is equal to 1. Right? Now, what do I need to do? I need to figure out what all of these values are, these letters here. And I've got 2 of them to be the same variable B. So it would make sense to maybe figure out what A is in terms of B, figure out what D is in terms of B, and then put them in there. And then obviously that would give us an equation all in terms of B, which we'd be able to find quite easily. And then once we know that, we can plug them in to find A, C, and D. So that's pretty much what you're doing here. Now, if I look at A now, we're going to use the same logic and principle that we used in part A to show that C was equal to 8 fifths B. We want to express A in terms of B, don't we? So we're just going to say, we're going to look for the probability of S, and then X is equal to, what was X equal to for A? That is 20, isn't it? And then we're going to equate this to the one for B, which we know is just K over 50 times B, right? K over 50 times by B. So if I use this here, well, for this one, we know it's going to be based on what we've got here. Let's just double check. Remember, we used it here. So for example, I'll just write here one more time just so it's super, super clear. I'm going to have probability of S given X is equal to 20 times by the probability of X is equal to 20, like this. And this is going to equal this intersection here. So I'll just write this out one more time just so it's super, super clear. And then doing this here, this one is going to be K over 20, right? Times by the probability of X equals 20, which is A from our table, right here. A. And then this is equal to K over 50 times by B, like this. So then I can just, I'm going to put this here. So I'm going to have K over 20 A is equal to K over 50 B, right? And then before I finish that, I'm just going to get the one for D as well, right? Because we need D in terms of a B as well, right? So doing the exact same thing, I'm going to write for D here. It's going to be the probability of, let me just double check, S given that X is equal to, for D, it was 100, right? 100. And we're going to times this by X is equal to 100. And then this will give us the intersection, isn't it? And then we're going to make this equal to the one for B, isn't it? So plugging everything in here, this is going to be K over 100, right? Times by D, isn't it? Right? Because that's what it is. That's fine. And this is going to equal this here, which is what we know is going to equal to the one for B. So we get these equations here. And then now we can just solve these to figure out what A in terms of B is and D in terms of B. So doing this one first, the K's will cancel again. I'm going to get 1 over 20A is equal to 1 over 50B. And that means if I times both sides by 20, I'm going to get 20 over 50B. And then cancel in the zeros, I'll get A is equal to 2 fifths B. And then doing this one here, this is going to be, K's will cancel again, 1 over 100. D is equal to 1 over 50B. Times by 100, I'm going to get D is equal to 100 over 50B. And that means that D is equal to 2B. So now I have A and D in terms of B. So what we can do now is just update this here. So I'll just copy this and put this here. So I'll just paste this here and bring this in here. So now we can update this and say, okay, well, fine. We know that A now. We know that A is 2/5 B. So I'm going to write 2/5 B plus B plus 8/5 B plus D, which is 2B. This is equal to 1. Now, this is all in terms of B, right? I can just figure out what B is, isn't it? So I've got 2/5 B and 8/5 B. That's 10/5 B altogether there. And I've got a B and a 2B, right? That's 3B. And this is equal to 1. 10 over 5 is 2, so I get 2B plus 3B is equal to 1, meaning that 5B is equal to 1, so therefore B is just equal to 1/5. Now I know what B is, I can figure out what A, C, and D are. Now remember, A was equal to 2/5 B, C was equal to 8/5 B, and D was equal to 2B, wasn't it? So now I can just plug in everything that I know, and that will give us our B. So this one here is just going to be 2 over 5 times 1 over 5. So this is going to give me 2 over 10. Sorry, not 2 over 10, 2 over 25, apologies. 2 over 25, this here. And then this one is just going to give me 8 over 5 times by 1 over 5, which is going to be 8 over 25. And then this one is going to be 2 times 1 over 5, isn't it? Which is just 2/5. So now we can just finish off and say that A is equal to 2 over 25. 2 over 25. B is going to equal 1/5. C will equal 8 over 25. And D will equal 2 over 5. And that will give you the full 5 marks. And that's that. So we've done that. Good stuff. Now, there was one more question. It was, let's see. It says, Nav tries a large number of times to throw the ball into the cup from a distance of 100 centimeters. He successfully gets the ball into the cup 30% of the time. For 1 mark, state given a reason why Tissam's model of this game is not suitable to describe Nav playing the game for all values of X. Okay, so let's have a look at what this actually means. Now, he's thrown the ball into a cup from a distance of 100 centimeters, and we know that they told us that Tissam stands X centimeters from the cup, right? So however far you stand away in centimeters is X. Since Nav is 100 centimeters away, it just means that this is just saying X is equal to 100, right? So we could use our probability distribution here to plug that in, right? So for example, I'm just gonna, because I've got room, I'll just do it here. I'll just do C here, right? So for C, we know that X is equal to 100, right? And what that means is, let's look at our formula here, because we've got an actual formula for successfully throwing the ball into the cup, right? It's the probability of S given that X is equal to X is equal to K over X, right? This is the formula here. Now, when I plug in X equals 100, I'm going to get probability of S, and then X is equal to 100, right? This is going to equal K over 100, isn't it? Right? And now they've told us that this happens 30% of the time. So we can actually just say that this is just equal to 0.3, isn't it? 30% is the same as 0.3. And then from this here, we can actually figure out what K is, because it's just going to be K is equal to 0.3 times 100. So therefore, we could say that K is equal to just 30. Yeah? We know that K is equal to 30. So since we know K is equal to 30, right, that means that we can actually figure out the probability of successfully throwing the ball into the cup from any of the distances away in centimeters, right? So bearing that in mind, right, we know that K is equal to 30. If I get this table right here, right, and for example, let's say I used it for X is equal to 20, it should give us the probability out. So now we know this here. How much room do I have? You know what I'll do? I'll just I'll copy this here one more time. So I'm going to copy this and put this underneath for C. I'll just do it here. I'll just do it here on this last page. Do it here. Whoops. Do it here. Okay. So we know now that K is equal to 30. So that means that our probability distribution is going to be the probability of S, and then X is equal to X is going to be 30 over X, right? Now, when X is equal to 20, right? That was the first one on the table. What will happen? Well, this will just become probability of S X is equal to 20 would give us 30 over 20, which is just 3 over 2, which is 1.5. Now, this is a problem because this is meant to be a probability. We know that probabilities have to sum to 1. So one of them cannot equal a number more than 1, right? So you could just say this is just greater than 1, which is impossible, right? Which is impossible, right? So the model would not work or would not be valid. And that will give you the 1 mark. And yeah, that's pretty much it for question 5. Yeah, we're done. Okay, so question 6 says a medical researcher is studying the number of hours T a patient stays in hospital following a particular operation. The histogram on the page opposite summarizes the results for a random sample of 90 patients. Part A says we need to use the histogram to estimate the probability that a patient stays between 10 and 30 hours for 2 marks. Okay, so what I'm going to do, let me screenshot this part A, and then let's go to our histogram that they're asking us for, which is right here. Let me just paste this here, and then let me bring this in here. Okay, so we need to work out the probability that a patient stays between 10 and 30 hours. So to understand this, right, what we need to do is, well, if I want to work out the probability that a patient stays between 10 and 30 hours, I would need the amount of patients that stay between 10 and 30 hours. So I'm going to just write n here just to denote that I'm looking for the number. I need the number of patients that stay between 10 and 30 hours divided by the total number of patients. And they told us that there were 90 patients. So it's going to be over 90. So what we could do is just use the histogram to work out how many patients there are between 10 and 30 hours. So this is not too bad. So let's look at this histogram. Now, you've got to be a bit careful here because the bars are not exactly on these points of 0, 5, and 10. So you just got to be a bit careful. So let's just work out the scaling. We can see that from 0 to 5, I've got how many boxes? I've got 10 boxes. So I'm going to say that 10 boxes is equal to 5, meaning that one box is just going to be 5 over 10, isn't it? Which is 0.5. So we know that every box is worth 0.5. So that will allow us to work out each of the areas that we need. So remember, we need it from 10 to 30. So let's break this down. So we're going to have to start from here. This here, we need to work out what this area is here, from here. And then we know that each box is worth 0.5. And there are 4 boxes from 10 to here. So this must be 4 times 0.5 is 2. This base here must be 2, meaning that this is 12 here. Now the base is 2 here. The height is just going to be the value of the frequency density, which is 4.2. So the height here is 4.2. So the area is going to be the 2 times the 4.2, which is 8.4. So I'm going to just put an 8.4 here. And this is the area between 10 and 12. Now, the next one, well, let's have a look here. We start at 12. And how many boxes do we have? We've got 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 boxes. 8 times 0.5 is 4, isn't it? So this must be a base of 4 here. Must be a base of 4, meaning that this is 16. So the base is 4. The height is also 4. Height is 4 here. So the area is going to be 4 times 4, which is 16. So that's 16. And then this one, 16 to 20 has a base of 4 again. The height this time, it goes up to halfway between 3 and 4 is 3.5. So the height here is 3.5. The area is going to be 4 times 3.5, which is just 14, isn't it? So I'm going to put 14 here. So we've got our areas between 10 and 20. Remember, we did between 10 and 30. So we've just got one more to do, which is 20 to 30 here. So we're going to cut off here. Now, what is the base here? The base, quite clearly, is just 10. Base is 10. And the height goes up to just 1 on the frequency density axis. So the area is going to be 10 times 1, which is just 10. So everything in the circle are just the frequencies between 10 and 12, 12 and 16, 16 and 20, and 20 and 30, and so on and so forth. So to get our answer, the one that we're looking for, remember, we're looking for the probability that a patient stays between 10 and 30 hours. We need the number between 10 and 30. So all we're going to do here is just add up these numbers, and that will give us the number of patients between 10 and 30 hours. So I'm going to go ahead and do that. So this will give us, let's just remind ourselves of the numbers. It's 8.4, 16, 14, and 10. So 8.4 plus 16 plus 14 plus 10. And then we're going to divide this by 90. And then we'll put this into my calculator and see what it gives me. So 8.4 plus 16 plus 14 plus 10 divided by 90. This is equal to 121 over 225. Or if you want to do it to three significant figures, this would be 0.538. 0.538. So either one of these would be fine. Okay, so that's part A. That's 2 marks. Let's go to part B. Part B says, for these 90 patients, the time spent in hospital following the operation had a mean of 14.9 hours, a standard deviation of 9.3 hours, and it says Thomas suggests that T can be modeled by a normal distribution where the mean is 14.9 and the standard deviation is 9.3. With reference to the histogram, state given a reason whether or not Thomas's model could be suitable. Okay, so Thomas is trying to model the patient staying in the hospital by a normal distribution, right? Now we need to reference the model to determine whether or not it's suitable. If we look at the histogram, right, which represents the patients. If I look at this here, and if you think about a normal distribution curve, right? I'll just do one here. It's like this, isn't it? Symmetrical, right? Symmetrical here, right? This histogram, right, isn't symmetrical, right? If anything, it's pretty much skewed. Because imagine if I was to approximate with a curve like this, it'll just be like this, isn't it? Right? Which is a bit skewed. So it'll pretty much be like this, right? Which is not suitable. So you could just say, just for part B, have I got room? I'll just do it here. So for part B, you could just say that the data is not symmetrical. Symmetrical. It is skewed. I can't spell today. It is skewed. So a normal distribution would not be suitable. That will be your answer for part B. So we'll go on to part C now. Okay, so part C says Zhang suggests that the frequency polygon based on this histogram could be modeled by a curve with equation y equals kx e to the minus x, where x is between 0 and 4, where x is measured in tens of hours, k is a constant. It says use algebraic integration to show that the integral of between 0 and n of x e to the minus x dx is equal to 1 minus n plus 1 e to the minus n for 4 marks. Okay, so what we have here is we've got an integration question in the stats paper. So that just goes to show you just need to be ready for anything, right? Even if you think you finished pure maths, you actually haven't finished it, as you can see. So let's go ahead and do this. Let me just screenshot this integral just so we don't need to keep going up and down. This here, and then let me just paste this here. Okay, now whenever you're dealing with integration, right, especially in year 13, as you guys are all aware, there are several methods of integration. There's integration by substitution, there's by parts, there's a reverse chain rule, so on and so forth, right? A key skill, and something I always tell my students, is to be able to identify what method of integration you're going to be using, right? With whatever they give you, right? So for example, this one here, when I look at it, I can see that I've got an x here, right? And then I've got e to the minus x here. Now, these are completely separate functions, right? They're two completely different functions. Now, what I'd always say to my students as well, you'd integrate this, right? The way to integrate this is think about how you would differentiate that. And you would differentiate that using the product rule, right? So because of that, it has to be by parts because by parts is derived from the product rule. So this is a by parts question. So for us to do this, we need to remind ourselves of the formula. So let's just go ahead and do that. So let's say if I have integral of u dv dx, this is going to be equal to uv minus the integral of v du dx, isn't it? So when you're doing by parts, you just need to identify what is your u, what is your dv, differentiate, integrate, and plug it into the formula. So based on what we have here, I'm going to say that our u, let me just write out here again, this is integral of x e to the minus x dx, right? I'm going to say that our u is going to be x, right? Just due to the fact that when I differentiate x, it gets me to 1, which is a lot simpler to work with. And then our dv is going to be e to the minus x, right? So I'm going to differentiate this one. This will give me du over dx. This will give me 1. And then if I integrate e to the minus x, remember how we integrate? We differentiate this power here, which is going to be -1, and then we're going to divide by that power. If I divide by -1, that's the same as multiplying by -1. So I can say v is going to equal minus e to the minus x. So this is what we've got here. Now we're in a position to just apply everything to the formula. So we're going to have u and v. It's going to be these two. So that's just going to be, all right, minus x e to the minus x. And then this is going to be, I'm going to take away, and it's going to be the integral of these two, right? V du. So these two multiplied together, that's just going to be minus e to the minus x dx. This is where we're at. Now, what I can do just to tidy up a tiny bit is that I've got a minus here. You can always bring a constant outside the integral. So if I bring that constant outside, then I have a negative here as well. Two negatives make a positive. So I can just simplify this a little bit to become minus x e to the minus x. And then I'm going to have a plus here. And then the integral of e to the minus x dx. Right? Now remember, let's not lose sight of what we need to show. We need to find what this is. And we have a definite integral as well. So this is where we're at. So what we need to do is apply our limits. So we're going to have 0 and n, because that's what the question asks for. X e to the minus x dx. And then remember, when you apply limits using by parts, this has no integral here. So you're just going to go straight away and put this into the square bracket. So I'm going to have minus x e to the minus x. It's going to be between 0 and n. And it's going to be plus integral of this one here. You're going to put the limits here, and then e to the minus x dx. All right, so we're here. Now, what you can do is, let's integrate this first, just so they both have we can put the limits on both. So if I integrate e to the minus x, that's just going to be minus e to the minus x, isn't it? So I'm going to have plus here. This is going to be minus e to the minus x, and then between the 0 and n. And then we are at this stage here. So minus x e to the minus x, and then between 0 and n. So where we're at. So just put this equals here. Okay, so we need to just evaluate now. Now remember what we need to show. Never lose sight of what you need to show, right? So let's go ahead and see what we get here. So when I plug in the limits, upper lower limit, I'm gonna have for the first one, it's gonna be minus n e to the minus n, and then minus, and then it's going to be 0. It's going to be minus 0, and then e to the minus 0. This is just going to cancel anyway, but I always just put it out. Just going to substitute all the values in anyway. And then that's done. And then now we need to do this one here. So I'm going to evaluate this one. I'm going to have minus e to the minus n. Then I'll take away the lower limit now. It's going to be minus e to the 0. So we get this here. I'm going to close these brackets. So now tidying this all, let's tidy all of this up and see what we get. So we're going to have a minus n e to the minus n. This here is just going to be 0, isn't it? It's going to be 0. So I'm just going to leave this here. I'm going to have plus, and then I'm going to have minus e to the minus n. And then I'm going to have these two negatives will make a plus. And then e to the minus 0 is just e to the 0, which is 1. So this is a 1 right here. So therefore, this is where I'm at. Got this here. Got minus n e to the minus n, and then we've got minus e to the minus n, and then we've got plus 1. Now remember, this is a show that question. Never lose sight of what you need to show. So let's just get this here. We need to show that we've got this. Let me just screenshot this here and then put it here, so I don't need to keep going up and down. So we are here so far. So we're nearly done. Now we just need to get this here. So let me just put this here. And then let's just see where we're at. So we need a 1 at the front, which we can have, I mean. So we can put 1 at the front. So we have 1, and then minus n e to the minus n, and then minus e to the minus n, like this. And then now they've got a factor of n plus 1, right? So something's been factorized. Now, when I look at what we've got here, if I look at these two terms on the end, I can see that I've got a factor of minus 1 here and here. And I've also got a factor of e to the minus n here, and then e to the minus n here. So I can actually take out minus e to the minus n from both of these terms. And what will happen is that I'll get 1. If I take out that factor of minus e to the minus n, like this, and then what will happen is that I'll be left with this term here. This is an n here, so it'll be an n here. And in this one, I've taken out the whole thing. So it's going to be a plus 1 here. So we've got that plus 1 that they want, and then as you can see, they've got e to the minus n on the other side. So all we're going to do is this e to the minus n, we're just going to move to the other side. So we're going to have 1 minus, and then it's going to be n plus 1. and then e to the minus n as required. So that's that. That is part C done. That's 4 marks in the bag. So let's go on to part D now. Okay, so part D says, show that for Zhang's model, k is equal to 99 to the nearest integer for 3 marks. Okay, so what I've done is I've just screenshot a couple of key facts that we need for this question here. So remember, Zhang suggested that the frequency polygon based on this histogram could be modeled by this curve, right? So when they're asking us for k is equal to 99, that is just referring to this k in this function here, right? Now he was just modeling the histogram. So remember, if we're modeling a frequency polygon based on a histogram, the frequencies have to remain the same, right? So if you think about it, we've got, if I was to do a frequency polygon, right, I would have to just join these up like this, the midpoints of each of these, and then join these up like this, right? And then if I want to try and make it into a curve, it's going to be something like that pretty much, right? So essentially what we have here is that we've got a curve. This is Zhang's curve here, goes like this, like that. And this here, it goes between 0 and 40 hours, right? This is the x-axis here. And remember, Zhang's model was measured in tens of hours, right? So it makes sense it goes between 0 and 4 because that's just going to mean 40 hours anyway. So 0 to 4. And then this is the model here. Let me zoom in a bit. This is the model here. Y equals k x e to the minus x, right? Now remember, the frequencies must remain the same. In this histogram, the frequencies represented the amount of patients, which were 90. So we know that all of these areas here must add to make 90 because that's the amount of patients. So if we have this frequency polygon which is representing that, this must mean that the area under this curve here must be 92, right? So we've got an area which we know is 90, right? And we've got an area under a curve. Well, how do you find the area under a curve in A-level maths? It's just definite integration. So essentially what we need to do here is we need to integrate between 0 and 4, right? 0 to 40 hours, right? And then we have to integrate this function here, kx e to the minus x dx, and this has to equal 90 because that's the amount of patients that there are. So all we need to do is just work this out. So let's go ahead and write this here. So we just zoom in a bit. So we've got the integral of k x e to the minus x dx between 0 and 4, and this is equal to 90. Now, how do I go ahead and integrate this? Well, first things first, I've got this constant k, right, which we know we can take out of the integral. So it just becomes k and then the integral of 0 to 4 of x e to the minus x dx. And we know that this is equal to 90. Now, remember what we just did in part C, right? We worked with something like this. We had to show that. Let's go and get it. We had to show that this here on the left was equal to that on the right, which is exactly what we have here. We just have a number in place of n. So let me just screenshot this here and paste this here and bring this here. So if I look at this here, and I compare this to what I have, right? Well, the only thing that's different here, I'm just going to highlight this in blue. This here, oops, my blue, there we go. This hair in blue, right, corresponds to this hair in blue, right? And we know that this is equal to that. But the only difference between what we have is that we've got a value for n now. It's 4, right? We've got n is equal to 4. So what we could say here as well, if n is equal to 4, I'm just going to mirror that here. So I'm going to have 0, I'm going to have 4 here, and then x e to the minus x dx. This will equal 1 minus, and then n is 4, so 4 plus 1, e to the minus 4. And then tidying this up here, this will give us 1 minus 5e to the minus 4. So we actually know what this here is equal to, this right here in blue. This is 1, do it here. This here is just 1 minus 5e to the minus 4. So what we can do here is, if I replace that there, then that will allow me to figure out what k is, isn't it? So I'm going to just put this here. I'm going to say we have k and then times, right, this expression here, 1 minus 5e to the minus 4, and this has to equal 90. So now we're in a position to find k because we just need to divide by that factor. So we're going to just say that k is equal to 90 over 1 minus 5e to the minus 4. So now I'm going to go ahead and put this into my calculator, and then let me just get rid of this. So this is just going to be 90 over 90 over 1 minus 5e to the minus 4 and this equals 99.07. Right, so I write this here, 99.07, blah, blah, blah. And to the nearest integer, that is just 99, isn't it? So we're done. And that's part D. Now let's go into part E and F. Okay, so part E says estimate the probability that t is between 10 and 30 using Thomas's model of t being normally distributed where the mean is 14.9 and the standard deviation is 9.3. Okay, this is just one mark. This isn't too bad. So all we're going to just do is just put this into our normal distribution calculator. So get my calculator here and we go to menu and go for distribution, go to normal CD, and I'm going to go to, what is it? The lower bound is 10, upper bound is 30. Our sigma is 9.3 and our mu is 14.9. So plugging this in, this gives us 0.64863 blah blah blah, which is just 0.649. So we could just say for part I, this is just equal to a probability of 10 and then t and then 30. This is just equal to 0.649. Okay, double I says that using Zhang's curve with equation y equals 99x e to the minus x and the answer to part C. Okay, so remember with Zhang's curve, right? Let's just get another sketch. Let's get a sketch here. Remember, Zhang's curve, right, was this one here. And remember, this curve tells us the number of patients, isn't it? Because the area under the curve is 90, the entire of the 90 patients, right? So if we want to estimate the probability between 10 and 30, what we need to do is work out the amount of patients between 10 and 30 hours, right? And in this case, because X was in tens of hours, that just means we need it from 1 to 3, right? So what we need to do to work this out is, well, if you think about it, if I want to figure out this area here, and it says that we need to use the answer to part C. So what we can say here is that I'll just do a little sketch here. If I wanted to work out the area between 1 and 3, then I could work out the area, right, from 0 to 3 first. And then once I work out that area, I can just take away the area from 0 to 1. So like this here. Oops, again. And then this here is going to be from 0 to 1. So if I do this one, take away this one, this will give me 1 to 3, wouldn't it? So all we need to do is just use our answer to part C now to work out what these integrals are. So let me do it on this side here. So for the first one, what we're going to be doing essentially is we're going to be doing 99 and then x e to the minus x dx, and we're going to be integrating between 0 and 3 because this will correspond to this area here. And then we will take away 99 and then the integral of 0, 1 of x e to the minus x dx, because this corresponds to that area there. We take those away, that will give us the number of patients between 10 and 30 hours, wouldn't it? So now it says we need to use part C as well. So remember in part C we had where was it? It was what was I looking for? Something here that I was looking for. It was right here. That's what I was looking for here. Remember, this is what we had in part C, right? So I'll get this here and put in this here. So we're just going to be working out these integrals here based on this, what we did last time. So in this case, for the one on the left, right, we can see then that it's just going to be 99 multiplied by, and then we could see that in our case, we've got n is equal to 3. So if n is 3 here, this would be 1 minus 3 plus 1, and then this would be a 3 here. So this is just going to be 1 minus 3 plus 1 is 4, so 4e to the minus 3. And then we're going to take away 99, and then we're going to do the exact same thing for this one here. Now, in this case, n is equal to 1. So if n is 1 here, then this will just be 1 plus 1, which is 2. So it's going to be 1 minus 2 e to the minus 1. And we're going to put this into our calculator and see what it gives us. So to put in this here, let me just zoom out so you can see everything as well. Putting this all in directly, this will give us, go back to, this will be 99 and then 1 minus 4e to the minus 3, and then close bracket, and then minus 99, and then it's going to be 1 minus 2, and then e to the minus 1, and then close bracket here. And then this will give us 53.124, blah, blah, blah. 1, 2, 4, blah, blah, blah. Now remember, this is not our answer. This is just an estimate for the number of patients between 10 and 30 hours. To get the probability, right? To get the probability using Zhang's model, what we have to do, right, is put this on the numerator, 53.124, blah, blah, blah. And then we're going to divide this by how many patients there were, which were 90. So we're just going to put this into a calculator and see what this gives us. So put this in here. It's just going to be answer divided by 90. This gives us 0.59, doesn't it? To three significant figures will be 0.59. This will be our answer here. So that's done. That's part E. Now part F said that the researcher decides to use Zhang's curve to model the probability between A and B. State one limitation of Zhang's model. Well, Zhang's model, right, if we remember it, was modeling the patients between, where can I go? I think it was here. Oops. Okay, we just go to the start here. Zhang's model, right, was modeling the patients between 0 and 40 hours, right? So a limitation would be, well, what if there are patients that need to stay longer than 40 hours? That would be a limitation. That's all you need to say, really. So I'll just put this here for the last one. Is to say for F, sorry. F, Zhang's model only goes up to 40 hours. 40 hours. And that's it. That's pretty much it. And this is stats finished. Hi guys, Daniel here. Hope you're doing well. So we've made it to the end of stats, and hopefully you didn't find it too bad. There was definitely a few tricky parts, especially the integration, as we can see. But yeah, you've just got to be ready for everything in these exams. So just hopefully that makes you aware that integration or anything in pure can come up in your applied exams. And yeah, we've pretty much done stats now. So now it's to go over to mechanics. So I'll be doing a separate video on that, and I may upload both of them at the same time, or may upload mechanics a bit after, but we'll see. But yeah, again, if you found the video helpful, found it beneficial, feel free to drop a like, comment, subscribe, share with your friends, anybody that you think that will find it beneficial. And yeah, again, thanks for all of your support, and I'll see you guys for mechanics. And also as well, I've got the pure ones too, which I'll put in the description. But yeah, take care. Thanks a lot for your support again, and I'll see you guys for mechanics. Bye bye.